Everybody, this is part 2 of solving through the 2019 E&M FRQ about the RC circuit. We're moving on to part D, where the switch is opened at time t equals 0. And this one's saying, hey, write but do not solve this differential equation that could be used to solve for the charge Q sub t on the capacitor as a function of time t after the switch is open. This one, I had to pause the video because I had to get more room to write this on, because I'm not going to be able to fit this one right here. But differential equations, we've got some things that are related right here, and what's related here is the current that's traveling through this, and the and the charge on the capacitor. So let's take a look. Now, this switch is open, so everything is essentially going to happen in here, which I think makes it a little easier to look at. And again, based on your questions today, I never plan my lessons out fully for like weeks in advance, because I say, what are the students doing? What are they asking questions about? And a lot of people are asking questions about these loops. So that's what our stuff is going to be on tomorrow, about some loop circuits. But here's the idea to get a head start on it. Or maybe today, if you're watching it today. Whoa, crazy. I kind of just choose a point on here and say, let me go through this whole circuit, because this charge is going to be coming off this capacitor. And what I know has to be true is that the sum of the volts equals 0. So this is where I'm going to set up my differential equation. So if I start right there and the current goes across that resistor, it goes minus I times 2R. That's the first voltage drop that happens across that resistor. Sorry for the shadow. Then I've got this resistor minus I times R. And then the voltage drop across the capacitor, and that would actually be a voltage gain across this capacitor, plus Q over C. And that's just the charge that's on the capacitor right now. And this will always be true. Even as you start to discharge and the current goes to 0, there won't be any charge left on here, and it'll just say 0, like negative 0 plus 0 equals 0, and that's fine. If I rearrange this, I see that Q over C equals I times 2R plus I times R, or I can say Q over C equals I times 3R. All the voltage you gain across the capacitor, you have to drop across those resistors. And then, all right, now it's differential time, and where is this going to be? Q as a function of t. Where will that show up? Well, with the current. That is dq dt, the rate of the flow of charge. Still times 3r, and then q over c. At this point, you might technically be done, but I'm usually in the business of getting these ready to solve, so I want to separate some variables here. And what I can do is put all my q's on this side, dq over q, and then bring that dt over here, so I'll integrate that from 0 to t at some point. And then this becomes 3rc. When we're integrating this, we would then say, oh, this is from some, like, time, the beginning 0 to some time t, and then some other charge to something else. We don't have to in this problem. We're done. Do not solve this any more than it asks you to do. dt over 3rc equals dq over q. Done. Because the problem is assuming that you have other things to do. So when it says do not solve in like those, it's not saying that it's too hard. You could do this. It would just take a little time, and then, but it's just a math problem. That's not bad at all. They just take a while. Here we've got bigger fish to fry. E, part 1, says calculate the current in the resistor immediately after the switch is opened. Okay. Well, one thing I know is I know in the beginning that capacitor has a charge of V naught over 3. I figured that out in part B before. So all that voltage is initially going to discharge across those resistors, those 3 resistors. So setting up that loop again, sum of the volts equals 0. And then I can say, what do I got? Plus V naught over 3 from the capacitors minus 2Ri minus Ri equals 0. Or V naught over 3 equals 3IR, just to flip that around. And that means that I here is going to equal V naught over 9R. Because all the voltage is stored here, which is V naught over 3, gets slowed down by those 3 resistors. And V naught over 3 divided by 3R equals that V naught over 9R. That's how our current starts. And then asymptotes to 0. Let me make sure I just did everything I had to. Sketch the current in the circuit as a function of time, to a long time. Explicitly label the maxima, check, with algebraic expressions. Did that as appropriate, and that's it. That's all I have to do to make sure that's done. And then, if the total amount of energy dissipated by the resistors after the switch is open, or is it greater than, less than, or equal to the amount of energy stored in the capacitor in part C. So, this capacitor has a lot of potential energy. All that potential energy we found, CV naught over 18, then gets released, and travels across, and that charge travels across these resistors. And that energy dissipates into heat. Any resistor is going to heat up as charges travel across it. That's that whole stuff from last year physics, where you could say, oh, the energy across a resistor is equal to I squared R times T, or delta V squared over R times T, or I delta V times T. And that's just saying that your energy is equal to your power for an amount of time. So all those resistors are going to heat up. But if I'm answering this question, if you looked at the solution guide, you said that you could either say less than or equal to if your justification made sense. Because some people said, look, the resistors, so if you said equal to, your thought is, yeah, that the potential energy stored in the capacitor, sorry for the shadow, is converted to heat energy. All those little charges that get moved, like, because the potential energy initially turns into kinetic energy as the charges move, but then as they make the resistor jiggle up and down, and they run into the edges of the resistor, they heat up the resistor. And that's assuming the wires have no resistance. And usually that's a pretty safe assumption, that R equals rho L over A. The resistivity of those wires is really small for metals. But it's technically not 0. The wires do heat up a very little bit, just not nearly as much as the resistors do. Probably 99.9% of your energy from the capacitor is converted into heat across the resistors, but technically, I guess that does mean less than. Because you might say, oh, the potential energy stored in the capacitor is going to heat across the resistors, and, so picking up from this statement, and the wires also dissipate or turn into heat energy sum of the UC into heat. So both were acceptable there, watching where that potential energy stored in that capacitor is going. That is that question. If you have any questions, follow-up questions after this, definitely let me know, because I want you to feel 100% good about a question like this. We have more stuff coming next on loops and using Kirchhoff's loop rule to solve complex problems. See ya!